Welcome to Relaxing Facts Studio. We are glad to have you here. This channel is a quiet space for calm exploration, gentle learning, and thoughtful observation of the natural world. In today's documentary, we will take a slow and peaceful journey into the ocean, its scale, its structure, and its steady presence across our planet. There is nothing you need to do and nothing you need to focus on closely. Simply listen, relax, and allow the information to flow at a comfortable pace. Let us begin. The ocean is not a single body of water. It is a connected system of seas and basins that move continuously around the globe. The Pacific Ocean alone is larger than all of Earth's land combined. Yet even this scale is difficult to truly imagine. Coastlines form only the edges of the ocean's influence. Far beyond the shore, water stretches uninterrupted for thousands of miles. Sunlight reflects differently depending on the angle of the waves, creating endless patterns of motion and light. Despite its size, the ocean operates with balance. Large currents move heat slowly from one region to another, helping maintain stable global conditions. These movements are not rushed. They unfold gradually over months and years. The ocean is structured in vertical layers, each defined by light, temperature, and pressure. The uppermost layer, often called the surface zone, receives sunlight and supports most visible marine life. Below this lies a dimmer region where light fades and colors soften. Deeper still, darkness becomes complete. These layers are not separate worlds, but connected environments, each influencing the next. Pressure increases steadily with depth, yet the ocean remains calm in its own way. Movement here is slow and deliberate. Even in darkness, life adapts quietly, shaped by consistency rather than speed. Ocean currents act like slow-moving rivers within the sea. Some flow near the surface, driven by wind and Earth's rotation. Others move deep below, guided by temperature and salinity. These currents transport energy around the planet. Warm water travels toward cooler regions, while cooler water sinks and flows back in return. This exchange occurs continuously, without sound or visible borders. Waves, by contrast, are surface expressions of energy. The water itself does not travel far. Instead, motion passes through it. This distinction reflects a broader pattern in nature: movement without displacement, change without disruption. Life in the ocean takes countless forms, from microscopic organisms to the largest animals ever known to exist. Each species occupies a specific role within its environment. Many marine organisms rely on efficiency rather than force. Shapes are streamlined, movements are minimal, and energy is conserved. This approach supports long-term survival in a stable yet demanding environment. Many life forms drift with currents, while others remain anchored to the seafloor. Together, they create systems that recycle nutrients and maintain equilibrium. There is no central control, only interaction and balance. Beneath the open water lies a landscape as varied as any on land. Vast plains stretch across the ocean floor, interrupted by mountain ranges, valleys, and deep trenches. These features formed slowly through geological processes. Tectonic movement, volcanic activity, and sediment accumulation all contribute over immense spans of time. Unlike land environments, these regions remain largely unchanged by weather. Their stability offers a quiet contrast to the dynamic surface above. The ocean plays a central role in Earth's natural systems. It absorbs and releases heat, influences weather patterns, and supports the water cycle. Evaporation from the ocean contributes to cloud formation and rainfall across continents. This process operates continuously, linking distant regions through shared atmospheric systems. By storing heat and distributing it gradually, the ocean helps reduce extreme fluctuations. Its influence is subtle but constant, supporting conditions that allow ecosystems to function predictably. Seawater is defined by its salinity, the concentration of dissolved salts and minerals. On average, ocean water contains about 3.5% dissolved material, primarily sodium and chloride. This balance developed gradually through erosion, volcanic activity, and long-term circulation. Salinity is not uniform across the ocean. In regions with high evaporation, such as subtropical zones, salinity tends to increase. In contrast, areas influenced by rainfall, river input, or melting ice often show lower salinity levels. These variations influence water density and movement. Slight differences in salt concentration can affect how water layers form and how currents behave, contributing to the ocean's large-scale circulation patterns. Ocean temperature changes predictably with depth. Near the surface, water temperature reflects sunlight, air temperature, and seasonal variation. Below this zone lies a region where temperature decreases rapidly, known as a transitional layer. Deeper waters remain consistently cold throughout the year. This thermal stability supports slow-moving circulation systems that operate on long timescales. The separation of warm and cold layers limits vertical mixing in many regions. As a result, heat energy is distributed horizontally over great distances rather than quickly dispersing downward. Tides are the result of gravitational interaction between Earth, the Moon, and the Sun. As Earth rotates, ocean water responds to these forces, creating regular patterns of rising and falling sea levels. Most coastlines experience 2 high tides and 2 low tides each day. The timing and range of tides vary depending on shoreline shape, water depth, and geographic position. Tidal movement plays a quiet but important role in mixing coastal waters. It helps redistribute nutrients and maintain water exchange between open ocean and shoreline environments. Coastal regions form the boundary between land and ocean. These areas are shaped by waves, tides, and long-term sediment transport. Sand, gravel, and organic material move gradually along shorelines in response to water motion. Beaches change slowly over time. Seasonal wave patterns can shift large amounts of sediment, reshaping coastlines without sudden transformation. Estuaries where fresh water meets seawater create unique conditions. Variations in salinity and depth support diverse biological communities adapted to gradual environmental change.
The polar oceans differ from other marine regions due to low temperatures and seasonal ice coverage. Sea ice forms when surface water freezes, creating floating layers that expand and retreat throughout the year. This ice influences light penetration and water movement. Beneath the ice, conditions remain relatively stable, allowing marine systems to function even during extended periods of darkness. Cold, dense water formed in polar regions contributes to deep ocean circulation, linking polar processes with distant parts of the global ocean. Sound travels differently in water than in air. Due to water's density, sound waves move faster and over longer distances beneath the surface. Natural ocean sounds include wave motion, rainfall, and subtle geological activity. These sounds form a continuous background, varying by location and depth. Because light diminishes with depth, sound becomes an efficient way information moves through marine environments, shaping interactions without visual cues. Many ocean processes occur over extended periods. Water masses may take hundreds or even thousands of years to complete large circulation paths. Sediment accumulates slowly on the seafloor, recording environmental conditions over long spans of time. These layers form natural archives of Earth's history. Viewed on a human timescale, the ocean appears constant. In reality, it is continuously changing at a pace defined by physics, gravity, and time, rather than immediacy. Despite centuries of study, much of the ocean remains unmapped in fine detail. Large-scale mapping relies on sonar technology, which uses sound waves to measure depth and seafloor shape. Light penetration decreases with depth, shaping where photosynthesis can occur and influencing vertical distribution of marine life. Many oceanic islands form through volcanic processes beneath the surface. Over time, repeated eruptions build structures that may eventually rise above sea level. Once exposed, these islands are shaped by wind, waves, and gradual erosion. Their life cycles span millions of years. Even after volcanic activity slows, islands continue to change as part of the broader ocean environment. For centuries, humans have crossed the ocean using observation, calculation, and later technology. Early navigation relied on stars, currents, and wind patterns. Modern navigation systems use satellites and precise instruments, yet they still account for ocean movement and variability. Navigation reflects cooperation with natural systems rather than control over them. Layers of sediment on the ocean floor accumulate slowly, preserving information about past conditions. These layers contain chemical and physical markers. Scientists study these records to understand long-term patterns without focusing on short-term events. The ocean stores this information quietly, maintaining a continuous record shaped by time and natural processes. Far from coastlines, the open ocean forms vast regions with limited direct influence from land. These areas are defined by depth, light availability, and distance rather than visible boundaries. Conditions here are generally stable. Nutrient levels are lower than in coastal zones, and biological activity follows slower cycles. The open ocean represents continuity, large spaces where change occurs gradually and predictably. At the ocean's surface, wind and currents influence the movement of floating materials. Natural elements such as seaweed and organic fragments drift over long distances.
Surface tension and wave motion shape how these materials gather or disperse. Over time, patterns emerge that reflect underlying circulation. These surface processes offer insight into how energy moves across wide areas without altering deeper layers. Gyres are broad, rotating systems of ocean currents found in major basins. They move slowly, guided by Earth's rotation and prevailing winds. Within a gyre, water circulates for extended periods. This motion influences temperature distribution and surface conditions. Gyres demonstrate how the ocean organizes movement across immense distances without sharp transitions. Seamounts are underwater mountains that rise from the ocean floor but do not reach the surface. Many formed through volcanic activity millions of years ago. These structures alter local water flow, often increasing mixing around their slopes. Although hidden from view, seamounts contribute to the ocean's physical complexity and long-term stability.
Vertical movement in the ocean occurs slowly. Differences in temperature and density allow water to rise or sink over time. This mixing redistributes heat and dissolved materials between layers. It is a gradual exchange rather than a sudden shift. Through this process, the ocean maintains balance across depths and regions. All major oceans are connected. Water moves between basins through narrow passages and deep channels. These connections allow properties such as temperature and salinity to influence distant regions. The ocean functions as a single system, shaped by continuity rather than separation. Many ocean processes repeat with regular timing. Tides, currents, and seasonal changes follow predictable cycles. This repetition creates reliability within natural systems. Organisms and environments adjust to these steady patterns. Over long periods, repetition supports resilience and stability throughout the global ocean. Wind plays a central role in shaping the ocean's surface. As air moves across water, it transfers energy through friction, creating ripples that may develop into waves. The strength, duration, and distance of wind influence wave size. These surface interactions distribute energy without significantly moving water masses forward. This continuous exchange between air and sea forms one of the most visible expressions of ocean dynamics. Although the ocean appears constant, many regions experience seasonal variation. Changes in sunlight angle and atmospheric conditions affect surface temperature. These shifts influence circulation patterns, biological activity, and mixing between layers. Seasonal cycles occur gradually, allowing marine systems to adjust without abrupt disruption. The ocean contains dissolved gases, including oxygen and carbon dioxide. These gases enter and leave the water through interaction with the atmosphere. Temperature and movement affect how efficiently gases are exchanged. Cooler waters generally hold more dissolved gas than warmer waters. This process supports long-term balance between ocean and air without rapid fluctuation.
The ocean contains invisible boundaries formed by differences in temperature, salinity, and density. These divisions shift slowly over time. They influence circulation and mixing, contributing to the layered structure of the ocean.
Materials in the ocean can travel great distances. Particles, nutrients, and organic matter move with currents over months or years. This transport connects distant regions, allowing substances from one area to influence another. The process occurs continuously and quietly across the global ocean. During calm weather periods, the ocean surface becomes smoother, allowing deeper processes to dominate. Reduced wind leads to limited surface mixing, increasing stratification between layers. These calm intervals contribute to the ocean's overall stability and predictability. Ocean systems are governed by balance rather than speed. Inputs and outputs of energy and materials occur steadily over time. This balance allows the ocean to maintain consistent patterns across large spatial and temporal scales. The result is a system defined by continuity, repetition, and gradual change. Water density in the ocean is influenced by temperature and salinity. Small differences in these factors determine whether water rises, sinks, or remains stable within a layer. Denser water tends to sink beneath lighter water, creating structured layers that persist over time. This stability limits rapid vertical movement. Density-driven organization allows the ocean to maintain predictable internal structure across large regions. Vertical circulation in the ocean occurs gradually. In some regions, surface water cools and becomes dense enough to sink, beginning a slow downward journey. Elsewhere, deeper water rises gently toward the surface over extended periods. These movements connect surface and deep layers without sudden disruption. Ocean absorbs a significant portion of the heat received by Earth. Due to water's physical properties, this heat is stored and released slowly. Surface layers warm and cool with seasonal change, while deeper layers remain stable. This heat storage moderates temperature variation across the planet in a steady, continuous manner. Strong currents often flow along the edges of continents. These boundary currents transport water efficiently over long distances that influence regional conditions by moving warm or cool water along coastlines. Despite their strength, these currents remain consistent and organized rather than chaotic. Modern ocean observation relies on instruments placed across wide areas. Buoys, drifting sensors, and satellites collect data continuously. These systems measure temperature, movement, and surface conditions over time. Long-term observation reveals patterns that are not visible through short-term study. Some parts of the ocean experience minimal disturbance. Far from storms and coastlines, conditions remain calm for extended periods. In these regions, slow processes dominate, and change occurs at a measured pace. Such areas highlight the ocean's capacity for stability and persistence. Although divided by names and geography, the ocean functions as a continuous system. Water properties and movement connect distant locations. Processes occurring in one region can influence another far away over time.
This continuity defines the ocean as a unified, long-term system shaped by physics and time. Water clarity in the ocean varies by location and conditions. In open ocean regions far from land, water often appears clear due to low concentrations of suspended particles. Clarity is influenced by microscopic organisms, dissolved materials, and gentle water movement. These variations affect how light travels through water and shape surface appearance without altering deeper structure.
The ocean's biological activity is driven by microscopic organisms. These tiny life forms float or drift within surface layers. Through simple chemical processes, they support larger systems by forming the base of marine food networks. Their activity occurs continuously and quietly, sustaining long-term balance across wide regions. The ocean follows natural rhythms shaped by Earth's rotation and orbital motion. Daily, monthly, and seasonal cycles influence movement and conditions. These rhythms create predictable timing for tides, temperature changes, and circulation patterns. Regular repetition allows systems to remain organized over extended periods. Seawater contains a wide range of dissolved substances. These elements move slowly between water, sediment, and living organisms. Chemical exchange occurs through gradual interaction rather than sudden change. This steady process maintains consistent composition across large volumes of water. Not all areas of the ocean experience frequent movement. Some regions remain calm for long periods. In these areas, slow accumulation and gentle circulation dominate. Calm regions act as stabilizing zones within the broader ocean system. Ocean regions are often defined by invisible transitions rather than physical barriers. Changes in temperature and salinity create gradual boundaries. These transitions shift slowly over time, reflecting underlying movement. Such boundaries organize the ocean while allowing continuous flow. Ocean systems persist through long spans of time. Their processes emphasize durability over speed. Energy transfer, circulation, and exchange occur steadily. This persistence allows the ocean to function as a long-term, self-maintaining system.